Hello, my fellow mathematicians. Root Beer here, looking at question 25, the last question on our 2010 Fermat paper from the fine folks at the University of Waterloo. Alex chose positive integers, a, b, c, d, e, f, and completely multiplied out the polynomial product. Yikes. Okay. Big, scary looking thing. Alright, but fine. Completely multiplied out that product. And, alright, well, we'll come back to look at that in a moment. After she simplified her result, she discarded any term involving x to the power larger than 6. Okay. And was astonished to see that what was left was 1 minus 2x. So, that means at the end of the day, she has, when she multiplies yikes out, she gets 1 minus 2x and then plus something. Well, they use an a, so let's call it p. Let's say p x to the 6 and q x to the 7 and r x to the 8, and it just keeps going on like this. But there's no x cubed term, no x4 term. Okay, and then so what does she do? She discards all these and she's left with 1 minus 2x. If a is greater than d plus e plus f, and b is greater than c plus d, and e is greater than c, what value of a did she choose? Whoa, okay. So, this is a very interesting polynomial question. Now, what can we see here? What indeed can we see here? So, just looking at there's probably a reason why they chose these polynomials. Now, things that I'm immediately noticing, the minus here. There's a minus here, and there's a minus here. So I'm betting these polynomials are going to be important to look at. I'm not so interested in the 1 that she finds just because everything has a constant term of 1. So, of course, we're going to have a constant term of 1. But the minus 2x, that's interesting. Something else to notice, just as I copy these down. Let's get rid of question 24 here. We got 1 minus x to the a, 1 plus x to the b, 1 minus x plus x squared, I think, to the c. Let's double check. Yeah. And just because I'm going to run out of space, I'm actually going to write these guys vertically. So the minus signs I'm definitely taking note of. Now, the worst thing to do, I think, would just to be sort of pick an a. Look at these answers. These a's are really, really, really big. Don't want that. So we don't want to just sort of pick an a and start expanding. But there might be some combinations we can do, and I'll touch on that in a moment. But I think there is a reason they chose these particular polynomials. 1 plus x squared. And 1 plus x squared plus x cubed plus x to the 4. Okay. So there we go. We've got all our expressions, and we need a 1 minus 2x at the end of the day. Now, the other thing they tell us is stuff like a is greater than d plus e plus f. Okay. And b is greater than c plus d. And I think the last one was e is greater than c. Okay. So this, to me, gives me maybe the hint that I should look at the stuff that a belongs to and the stuff that d, e, and f belong to. Or E and C, for example. These guys might pair up quite nicely in an interesting way. Okay, so I think that's probably going to be my first goal. We might say something like E is C plus some positive amount. I'm going to reuse P because otherwise I think I'm going to run out of letters. So P is greater than 0. So that means 1 minus x plus x squared to the c times 1 plus x squared to the e is going to look like 1 minus x plus x squared to the c. But e is c plus p. So we get 1 plus x squared to the c. And then we'll get some extra copies of 1 plus x squared to the p. But this is 1 minus x plus x squared times 1 plus x squared all to the c. And I think that might turn into something more important. What is that product? I'm going to switch back to black here. So we get 1 plus x squared. I'm just expanding this out. And then we'll get minus x squared minus x cubed. Then plus x squared plus x cubed plus x to the 4. Cancels. And now here's the thing. All the minus signs that I was getting from, that I might potentially get here that would give me a 1 minus 2x, they're sort of canceled out. They're already absorbed in this part, and so I don't get any minus signs. Very interesting. So the C stuff here does not contribute to this minus sign. It's got to all be the 1 minus x. That's where the minus sign for the 1 minus 2 has to factor in some way. Because if it wasn't there, if this were somehow like a 1 plus x or 1 plus 3x, just to make it different from the one below it, knowing that the C copies here of 1 minus x plus x squared pair up with the 1 plus x squareds to give us all positive, you'd have no minus signs anywhere. Everything would just be 1 plus 5x's plus 7. It would all be plus positive numbers. So the minus sign has to come from this A part. Okay. Now, I don't know exactly how that's going to fit into things. No idea there yet. But I've only used one piece of information here, the E greater than C stuff. Okay. What else can we say? Well, there's certainly x's that can come from the leftover 1 plus x squareds to the p. So that's certainly where some x terms can come from. Now, they'll all be positive. But here's what I'm thinking. I'm thinking that if you expand all this out, thanks to the 1 minus x to the a, when you collect like terms, you'll get a whole bunch of like maybe negative 52 x's. And then from all the other stuff with all their x's left over, you'll get maybe, what did I say, 52 minus 52 x's. You'll get 50 x's, and then those will cancel out to give you the minus 2 x's. So I think we should be keeping track of where x's are. Now, as soon as you get 1 plus x squared with no x terms, that's not really going to come into play at all. Not at all. So, or at least the x squared and the x to the 4 are too big. So, let's continue this sort of combining work with the b here, 1 plus x. Now, b is greater than c plus d. Is there a way to match those ones up? I'm not... They should, but I think they will still... I think they'll I want to focus on the A for a moment, just because A being greater than D, E, and F, A times the 1 minus X times the stuff that's raised to the F certainly rings a bell. Same with E. Not so much with D, unfortunately, but that's okay. Things to think about. I'm also wondering, is there a way to combine these inequalities? Something like A plus B. Yeah, I don't know. Okay. Let's just say A is equal to D plus E plus F plus, again, I'm just going to borrow a letter I'd already sort of used, just because otherwise I'm going to run out of letters. But he's d plus e plus f plus q. So I can take 1 minus x to the f and multiply it by the 1 plus x squared plus x cubed x to the 4. I think we're going to slowly, this is going to be, everything will cancel out. You'll get 1 minus x to the 5, which will still have minus signs, but they'll be minus x to the 5s, and they won't contribute in any way. I think we're going to slowly rearrange the original expression, the one given to us in the problem, and turn it into something that's a little nicer to tease out the term, the coefficient of x and things like that. Okay, so that's true. And then you also have 1 minus x to the e. Now, e is actually, so let's be careful. E is c plus p. So we could also say, so your q is greater than 0. But this is also d plus c plus p plus f plus q. So we get f copies of 1 minus x to pair up here. We get p copies to pair with the 1 plus x squared to the p. And that turns into 1 minus x cubed. Again, sort of taking out the power of these terms to have any effect on when we expand everything out, creating this 1 minus 2 to the x stuff. And then d and c. Now d and c, d and c, that's related to b, isn't it? Interesting. Don't quite know how to use that, because if b were less than c plus d, then I'd say some of the things in a compare with the things in b. But, Well, let's start. I feel like we're going to get some 1 plus x's left over. We're certainly going to get some 1 minus x's left over. We have to, otherwise we don't get the minus sign for 1 minus 2x. But what can we actually do? So I could say something like b is c plus d plus r, and r is greater than 0. And then I compare 1 minus x and 1 plus x with stuff coming from c and stuff coming from d. Except I already ate the ones coming from c, so I don't know as I necessarily... So I can get c of those, and c of those are free. And then we've got c of these, because we combined those on the previous page. Now we get 1 plus x squared plus x to the 4 to the c. So we've got that lying around, then we've got c copies of 1 plus x, c copies of 1 minus x. That's difference of squares, so that's going to be 1 minus x squared to the c, and that turns into 1 minus x to the 6 to the c, 1, 1, and then the minus 1, and that cancels. Yeah. So 1 minus x to the 6 to the c. That's the first x to the 6 we've seen, which is kind of nice. Okay, and then d. A and b and d can pair up. So what would that do? So d copies of 1 minus x are free, d copies of 1 plus x are free, and then the heck was d? I think it was 1 plus x. But again, that turns into something really, really nice. So we're getting a lot of 1 minus x to the stuffs. And then we're just going to be left with q copies of 1 minus x and r copies of 1 plus x. And which one is bigger? I'm pretty sure the q has to be bigger than the r. but let's not get into that right now. So let's just very, very carefully make sure that we've done the right thing before we move on to the next part. But here's what I think we've got. A can be written as D plus, and C can be written as, or E can be written as C plus P. So D plus E plus F plus a little bit more. B can be written as C plus D plus a little bit more. C is what it is. D is exactly what it is, so plus x squared. E was 1 plus x squared, so that's to the E, but E is C plus P. And then we had 1 plus x squared plus x cubed plus x to the 4 to the f. Okay. So let's see if we can follow this together. So the q, we get 1 minus x to the q. I'm really enjoying the colors we've got here. And then r, we got 1 plus x to the r. All right. Now, the C's. All of these combined to make 1 minus x to the 6. The D's combined to make 1 minus x to the 4. The ones with P combined to make 1 minus x to the 3. And the last one here, what color I haven't used, the medium blue, the F's combined to make 1 minus x to the 5. All right. So this is looking like a nicer expression. It also, if you know these sorts of things, looks a lot sort of like, I think what we're using here is cyclotomic polynomials, which is something you can look up if you're interested in, but it's not really for math contests. Cyclotomic polynomials. I haven't mentioned it already because I didn't want it to influence me, but I did sort of notice that these polynomials were like that. They're used for roots of unity in sort of field theory, but they're nothing you really need right now. But they've got some interesting properties and some very weird applications, like an interesting pair of dice that I might talk about someday. But, you know, if you're interested in these sorts of things, they're kind of nifty. But, yeah, all we've done is basically take the statement they gave us, recombined it into what I would say are much nicer looking polynomials to deal with. Okay. Now, again, we're focused on this, the minus signs, minuses and x's. So 1 minus x to the q. This expands out as 1 minus qx plus q times q minus 1 over 2x squared. I don't really need most of this. The next one will be minus something to the x to the 3, and so on. Okay. Now, when we multiply everything together, the end result is going to be 1 minus 2x plus a bunch of stuff that is x to the 6th, x to the 7th, x to the 8th. So nothing we really need to worry about. So where can the x to the where can the 1 minus 2x come in? What contributes to a 1 minus 2x? Well, the 1 here times the 1 when you expand this, the 1 when you expand this. So also, I guess, this here turns into 1 plus r copies of x plus r minus 1 over 2 x squared plus, and that keeps going on. And we can do that for the other ones, but here's my point. I don't think it's going to make that big of a difference. Because in order to get a copy of x towards the end, you have to... So, okay. Say I want to multiply these out. But I'm only interested in what the constant term is and what the multiple of x is, the coefficient next to x. It doesn't make... No one cares what happens to 3x. So 3x gets multiplied here, and multiplied here, and multiplied here, and multiplied here, and it all gets added up. It's a rich tapestry, but we've already got too many x squareds for this to ever contribute to what the linear term is. So to figure out what the linear term is, you can actually ignore these parts and say, all right, 1 minus 2x times 1 plus 4x, that's going to get you a 1, minus 2x plus 4x, and then there's minus 8x squared, but we don't care about that. And so the linear term here is 2x. But the bigger terms don't matter. And it's sort of like modular arithmetic for powers of x, almost. So, in a certain sense, 1 minus x to the 6 to the c, it's going to look like 1 minus cx to the 6 plus c times c minus 1 over 2, x to the 12, and things like that. But we don't really care about multiplying any of our stuff by the x to the 6 or the x to the 12 parts, because that's going to make it too big. Way too big. Okay? So, I think in terms of that, in terms of just figuring out the linear term, all we care about is the 1 minus qx and the 1 plus rx. So, and get these guys squared away. I'm just writing plus higher terms. I know they're there, but I'm not interested in them. And then we've got 1 minus higher terms. Or plus higher terms. And so this is the 1 minus x to the 6 to the c. It's going to expand into 1 plus a bunch of stuff that's too big for me to care about. Same with the other ones. And so when it comes to sort of expanding this out and foiling it out, or whatever you want to call it, we're just going to get 1 minus qx plus rx plus, or sorry, minus qrx squared, and then plus a bunch of higher terms. Now, these aren't irrelevant. We're going to get into that in a moment, but I know that this has got to equal 1 minus 2x plus a bunch of stuff that is x to the 6 times some polynomial. And so the only way we're going to get x's is right here, so minus 2 is equal to r minus q. Or rather, q is r plus 2. Okay? And that might in some way be important. So that q really, so a really is bigger than b and stuff like that. So, now I'm at a crossroads. Do I... So I still don't know what q is. That in fact, I don't need to know what q is. I need to know what a is, right? Yeah, what a did she choose? Okay, we're not there yet, but... What is A? A is D plus C plus P plus R plus Q. Or sorry, F plus Q. And that's almost all the numbers represented here. I can change I can change Q into R plus 2. So, here's what we can say. A is R plus 2, that's the Q part, plus P plus C plus D plus F. Okay. Pretty sure, just gotta go back and double check that. Okay. D plus C and F, P and Q, but Q is now R plus 2. Alright, we're happy with that. And then what have we got here? We've got 1 minus x to the r plus 2. We've got 1 plus x to the r. I'm going to combine these in a moment to get 1 minus x squared. But I also have 1 minus x, 6 to the c. I know it's 1 minus x to the 5 to the f. 1 minus x cubed and 1 minus x to the 4 were in there. I don't remember off the top of my head which ones they were. I think this one's p. And so by process elimination, this one's d. If we just go back and double check, yes, that's right for the d and the p there. Okay. So, what have we got here? Well, this part here combines to 1 minus x squared to the r, and we get a 1 minus x squared. Okay. So, just carefully rewrite that. And then we've got a lot of this higher term stuff in all the variables that I'm going to order them from top to bottom, from increasing to decreasing. So that's to the p, 1 minus x to the 4 to the d, 1 minus x to the 5 to the f, and 1 minus x to the 6 to the c. And I don't think it's a coincidence that we're talking about terms of x to the 6 larger than x to the 6. So that's actually, starting x to the 7. So it's 1 minus x, 2x plus something x to the 7 plus something x to the 8. So it's not a coincidence that there's that 6 and that this 6 is the highest thing we've got. We just have to sort of be careful about this. So we know 1 minus 2x just comes from this bit. But it also brings an x squared to the table. Now, these last 4 are too big for x squareds. Mod x squared, we might say they are the same as 1. But we get some x squareds here. So we have to be careful. So this guy here is 1 minus rx squareds plus more stuff that's bigger than x squared. It's like x to the 4s and x to the 6s and stuff like that. So when I multiply these out, I need my x squareds to cancel. And this will help me figure out what r has to be. So I get 1 minus 2x plus x squared, and then minus rx squared minus 2rx cubed, plus 2rx cubed, and then minus rx to the 4. Okay, so those have to cancel. So r is equal to 1. And then this turns into 2x. So what we've got by expanding this part out looks like 1 minus 2x plus 2x cubed minus x to the 4. And now those have to be dealt with by canceling out with things like the p part and the d part. And we're going to be able to figure out p, d, and f, and c. It's going to be fantastic. So in general, just because I keep using this property, 1 minus x to the m to the n, in fact, 1 minus y to the n, looks like 1 minus y, or minus ny. This is standard expanding binomial terms and things like that. Plus y squared, plus other stuff. But for all of these, we're beyond the x to the 2, we're not going to need to deal with them because they're going to be bigger than x to the 7, or bigger than x to the 6 in terms of the exponent. Because if I put in x to the 4 here, x to the 4 squared is x to the 8, and so I don't actually care what that value is because I know it doesn't have to necessarily be 0. So this is what we're using, and so in general this is 1 minus n x to the m plus n times n minus 1 over 2 x to the m squared, or x to the 2m, plus more stuff. So that's what we keep using. So where are we? We've got 1 minus x to the 2. We've got 1 minus x squared to the 1. And then we got 1 minus x cubed to the, what was it? P. 1 minus x to the 4 to the d. 1 minus x to the 5 to the f. 1 minus x to the 6 to the c. Okay? So this part here looks like 1 minus 2x plus 2x to the 3 plus, or sorry, minus x to the 4. And then what have we got here? Well, when we expand it out with 1 minus px to the 3 plus 2p, or no, not 2p, p times p minus 1. Right, did I compute the earlier one correctly? Yeah. Okay. P to the x, and then it'll be something x to the 6 that I'm not particularly interested in right now. When that expands out, then I'll get 1 minus 2x plus 2x to the 3 minus x to the 4 minus px cubed plus 2px to the 4 minus 2px to the 6 plus p, well, it doesn't really matter at that point. But these two have to cancel out. So p is equal to 2. And what we really have now is 1 minus 2x. Those cancel out. You'll get a minus x to the 4 plus 4x to the 4. So that'll be plus 3x to the 4. Okay. And if p is equal to 2, then this really does give me a 6 here. All right, I'm happy with what I've done, but I think I haven't actually expanded this part out correctly. It's fine for the first little bit, but so p is still equal to 2, but we're gonna have to be a little more careful. So p is 2. So we got 2, 1, 2. It's slow going, but it is working. So 1 minus x squared. 1 minus x squared to the 1. 1 minus x cubed to the 2. 1 minus x to the 4 to the d. 1 minus x to the 5 to the f. 1 minus x to the 6 to the c. All right. So let's expand this out. This is 1 minus 2x plus x squared times 1 minus x times... I feel like there might be a faster way to do this, but I can't think of it off the top of my head. Maybe multiplying by 1 plus x's or something somewhere. No, I don't think that'll work. 2x cubed plus x to the 6. So expand this out. 1 minus 2x plus x squared. Minus x squared plus 2x cubed minus x to the 4. Oh, look at that. I was actually correct. And then that part cancels. Multiply that with 1 minus 2x cubed plus x to the 6. And you get 1 minus 2x plus 2x cubed minus x to the 4 minus 2x cubed plus 4x to the 4 minus 4x to the 6 plus 2x to the 7, but I don't care about that. And then plus x to the 6 minus 2x to the 7, but again, I don't care about that. We're just keeping track of the powers of x that are less than or equal to x to the 6. All right. So those cancel, and I'm left with 1 minus 2x plus 3x to the 4 minus 3x to the 6. Great, fine, fantastic. So now that gets multiplied by the 1 minus dx to the 4 plus yada yada yada. You'll get 1 minus 2x plus 3x to the 4 minus 3x to the 6 minus dx to the 4 plus 2dx to the 5. Those have to cancel out, so immediately I see d is equal to 3. And so we can start expanding things out. I don't need any more terms because this would be something x to the 8 and something x to the 12. So I think that's going to simplify our work a little bit more. But we get 1 minus, here we go, 1 minus 2x plus 3x to the 4 minus 3x to the 6. Times 1 minus x to the, oh gosh, what was it, 4 to the 3. Okay. But, sort of mod x to the 6, this guy is really just minus 3x to the 4. And similarly, the other ones are minus, oh gosh, what were they? F x to the 5, because the bigger terms here don't matter, and this one's minus c x to the 6. I think this will actually make it go a lot faster here at the end. So this part here turns into 1 minus 2x plus 3x to the 4 minus 3x to the 6 minus 3x to the 4 plus 6x to the 5 minus, and then these two will combine to an x to the 8 that I don't care about, and the other ones will be an x to the 10 that I don't care about. So those cancel. So I'm left with this part here is 1 minus 2x plus 6x to the 5 minus 3x to the 6. Multiply that by 1 minus fx to the 5. Basically, you're just going to get some stuff plus x to the 5 and then a minus fx to the 5. So f has got to be equal to 6. Fine. So f equals 6. So we can use that and expand this out. 1 minus 2x plus 6x to the 5 minus 3x to the 6 minus 6x to the 5 plus 12x to the 6 minus 36x to the 10, but no one cares. So these cancel out, and we're left with 1 minus 2x plus 9x to the 6, essentially, times 1 minus cx to the 6. This will be 1 minus 2x plus 9x to the 6. Minus cx to the 6 plus a bunch of other stuff that's way too big to consider. C has got to be equal to 9. So we get 9, 6. What were the other ones? 9, 6, 3. D was 3, so 9, 6, 3. So that's 18. Plus, oh, I had the exponents listed up there. So this guy turns into a 3. This is a 6. This is a 9. 9, 6, 3 is 18. Plus 2 is 21. So we should get an answer of 23. A is 23. It has taken us a while, but there we go. 2 plus 1 plus 2 plus 3 plus 6 plus 9. Please let 23 be one of the answers. There it is at the end. So that's an answer of E. And that squares everything away quite nicely. Took us a while, but I really liked that the question started out really naturally. They gave us just enough information to push us in the right direction. The minus sign sticking out like a sore thumb with the 1 minus 2x said, hey, focus on these minus parts. The A being greater than D plus E plus F to me suggested, okay, I've got a lot of these factors, not so many of these factors. These ones can pair up with these and cancel a bunch of stuff out. And that worked out really nicely. We got a whole bunch of really easy polynomials to work with. Okay, so that was really good. I really liked that question. Long, and I think maybe a little too hard, but it's question 25. That's the one that they're allowed to just be ridiculously hard, because there are some people out there who say, no, that's too easy. So, Everyone likes a challenge. But that finishes off our Fermat paper. It is all done. That's the last question. So up next, 2010 Euclid or things in the future. If you're looking for more Fermats, I've got a whole bunch on my channel, but the 2011 will be coming up. The Hypatia 2010 is a contest from the same year, aimed at the same grade level, but is written. So there's lots of stuff to look forward to or look into. And yeah, thank you guys so much for watching. As always, I really appreciate it. Feel free to leave a comment, like, or subscribe just to show your support. They're sort of like virtual thumbs up, and so I know people are listening and interested. But yeah, that's it for me. Have yourself a wonderful day, and I will see you in another math video at another math time.